The oldest light in the universe contains a region that appears colder than it should be. Current cosmological models suggest small temperature variations across the cosmic microwave background, but not a massive cold scar extending across such a large region of space. The anomaly first appeared as a faint temperature depression inside high-precision microwave observations of the early universe. Instead of blending smoothly into surrounding radiation patterns, the region stood out as an unusually coherent cold imprint embedded within the background itself. Under standard inflationary models, temperature fluctuations should distribute statistically across the sky without producing extreme large-scale irregularities. The cold spot appears to push beyond what those probability distributions would normally predict. The physical system behind the observation is the cosmic microwave background, a relic radiation field released shortly after the early universe became transparent. Tiny variations in this radiation preserve information about density conditions that existed billions of years before galaxies formed. Most fluctuations inside the microwave background remain small and statistically consistent with cosmological expectations. The cold spot differs because its temperature deviation extends across a much larger angular region than surrounding structures. One explanation proposes that the anomaly may not originate from the early universe itself. Instead, large-scale structures between Earth and the microwave background could distort the radiation during its journey across space. In this interpretation, the radiation may have crossed a massive underdense region, sometimes referred to as a supervoid. As photons move through that expanding low-density structure, they could have lost slightly more energy than expected, leaving behind a colder microwave imprint. The mechanism depends on gravitational evolution across cosmic time. Expanding voids alter the energy balance experienced by traveling radiation, potentially imprinting secondary temperature distortions onto the microwave background. But measurements of known void structures appear insufficient to fully account for the scale and depth of the observed temperature depression. The detected cold region may exceed what current void models can reproduce through ordinary gravitational effects alone. That creates the first major theoretical split. If foreground structures cannot generate the anomaly completely, then the origin of the cold spot may reach back into conditions present during the earliest stages of cosmic evolution itself. A competing theory suggests the anomaly could reflect an unusually rare primordial fluctuation generated during cosmic inflation. In this framework, the cold spot would not require new physics, only an extreme statistical event emerging from quantum fluctuations in the infant universe. This explanation preserves the standard cosmological model without introducing unknown mechanisms. However, the probability calculations remain uncomfortable because the observed structure appears larger and more coherent than typical inflationary fluctuations are expected to produce. The tension deepens because statistical rarity alone does not fully explain why the region appears spatially organized instead of randomly scattered. The cold spot looks less like isolated noise and more like a large-scale feature with internal structure. Some researchers therefore explored whether the anomaly could indicate incomplete assumptions within inflationary theory itself. Certain modified inflation scenarios may produce non-standard fluctuation patterns capable of generating unusually large temperature depressions. These models attempt to reproduce the observed microwave imprint without relying entirely on statistical coincidence, but they often introduce additional assumptions that remain difficult to verify observationally. Another possibility suggests the anomaly could emerge from unresolved systematic effects within observational reconstruction. Microwave background maps require complex foreground subtraction processes to remove contamination from galaxies, dust, and local radiation sources. If residual contamination survived inside the reconstruction process, it could distort the apparent temperature distribution. Yet, repeated observations from independent instruments have continued to preserve the cold spot signal with broadly similar characteristics. That persistence weakens the idea that the anomaly is merely an observational artifact. The The feature continues to appear even as instrumentation calibration methods and data processing techniques improve over time. The cold spot also creates a deeper conceptual problem for cosmology because the microwave background serves as one of the strongest observational foundations of the Standard Model. Large, unexplained irregularities inside that framework carry disproportionate theoretical weight. Most cosmological predictions depend on the assumption that large-scale temperature fluctuations remain statistically isotropic across the observable universe. The cold spot appears to strain that assumption without clearly violating it outright. This ambiguity makes the anomaly difficult to classify. It is not extreme enough to definitively overthrow current cosmology, yet it remains unusual enough to resist clean absorption into existing expectations. The observational pattern becomes even more difficult to dismiss because the anomaly exists at universal scale. Unlike localized astrophysical events, the cold spot is embedded directly into relic radiation spanning the observable cosmos itself. That scale changes the stakes of the interpretation. If the anomaly reflects unknown early universe physics, then the underlying mechanism may connect to processes operating near the origin conditions of cosmic structure formation. But if the anomaly emerges from line-of-sight gravitational evolution instead, then current models of large-scale cosmic structure may still contain unresolved limitations. Both interpretations preserve part of the existing framework while exposing weakness elsewhere. Neither theory fully closes the gap between observation and expectation. Primordial explanations struggle with probability and verification, while foreground structure explanations struggle with energetic sufficiency and observational consistency. As more precise cosmological surveys continue to refine measurements of background radiation and large-scale structure, the cold spot remains suspended between competing interpretations. It still appears as a cold scar in the oldest observable light of the universe, and current models have not fully explained why it exists at all. The difficulty becomes clear when the cold spot is compared against the surrounding microwave background at full cosmic scale. Most neighboring fluctuations dissolve gradually into statistical noise, but this region maintains a colder and more coherent structure across an unusually broad area. That persistence creates a propagation problem. If the anomaly emerged from an ordinary fluctuation inside the early radiation field, its large-scale coherence may require conditions that standard inflation models do not naturally amplify to this extent. The microwave background itself is observed as a nearly uniform radiation shell surrounding the observable universe. Tiny deviations exist everywhere, but they usually balance statistically across large angular scales. The cold spot does not disappear under that averaging process. It remains visible even when temperature maps are smoothed over progressively larger regions. This raises a deeper limitation in observational cosmology. The microwave background can only be measured from one cosmic vantage point because every observation is constrained to a single observable universe. That means the anomaly cannot be tested against alternative cosmic realizations. Current models depend heavily on statistical expectation, yet there is no second universe available for direct comparison. The uncertainty therefore propagates beyond the anomaly itself. If the cold spot represents a rare fluctuation, cosmologists may simply inhabit an unusually improbable realization of the universe. But if it reflects incomplete physics, then the standard statistical framework may already contain hidden structural weaknesses. Both interpretations preserve the same observation while assigning failure to different layers of the model. The tension sharpens because the anomaly exists inside relic radiation that predates galaxies, stars, and large-scale structure formation. Whatever generated the temperature depression may have originated before most visible cosmic architecture even existed. That early timing introduces severe measurement limits. Conditions during primordial expansion cannot be recreated directly, and surviving evidence reaches observers only through residual radiation patterns billions of years later. The signal is also extremely weak in absolute terms. The temperature difference corresponds to tiny microwave variations measured only fractions of a degree above absolute zero. Yet those microscopic deviations scale upward into universal implications. A minute imbalance inside primordial radiation may point toward large-scale incompleteness in the way the early universe evolved. Some inflationary interpretations attempt to contain the anomaly by treating it as an acceptable statistical outlier, but that solution depends on probability thresholds that remain sensitive to how the background itself is modeled and filtered. The problem is not merely that the cold spot is cold. The deeper issue is that its shape, coherence, and scale appear unusually aligned compared to surrounding fluctuations. That distinction becomes visible in observational reconstructions. Random microwave irregularities generally fragment into smaller, distributed patterns, while the cold spot preserves a more organized depression extending across a large angular region. If foreground void structures contribute to the effect, the required energy evolution must propagate across immense intergalactic distances. The gravitational environment along the radiation path would need to influence photons consistently over billions of light years. Current surveys have identified underdense regions near the observational direction of the anomaly, but the measured density deficits still appear too weak to fully reproduce the observed temperature contrast through known large-scale gravitational effects alone. This creates an analytical fracture between scale and mechanism. The observable structure may exist, but its measured influence does not seem proportionate to the microwave imprint it supposedly generated. As cosmological mapping improves, the contradiction becomes harder to isolate cleanly. Better data narrows some uncertainties while simultaneously tightening the limits on explanations that once appeared viable. The anomaly therefore grows more restrictive over time rather than less. Each refinement removes portions of parameter space without fully eliminating the cold spot itself. Even the boundaries of the structure remain difficult to define precisely. Different filtering methods slightly alter the measured dimensions and significance of the region, changing how anomalous it appears statistically. But across those variations, the central observational feature survives. A large cold imprint remains embedded inside the oldest observable radiation in the universe, and no single interpretation has fully absorbed its implications into a stable cosmological explanation. The cold spot has therefore shifted from a simple temperature irregularity into a boundary problem inside cosmology itself. Current models can describe the microwave background with remarkable precision across most of the observable universe. Yet this region continues to resist clean statistical or physical integration. Some explanations may partially account for the structure through large-scale gravitational evolution. Others may reduce the anomaly to an extreme primordial fluctuation, but neither interpretation fully closes the gap between the observed microwave imprint and the expectations generated by standard cosmological behavior. That unresolved gap matters because the anomaly is embedded directly inside relic radiation from the early universe. If the cold spot reflects incomplete inflationary assumptions, then the limitation exists near the foundation of modern cosmology rather than at its edges. And if the anomaly instead emerges from foreground structure interactions, then current models of large-scale cosmic evolution may still underestimate how radiation changes while crossing the universe itself. The oldest observable light in existence still contains a cold region that current physics does not explain cleanly.